So today I'm going to unbox and play around with Fluke's 8.5-digit reference multimeter. And I wouldn't normally do an unboxing video, but this is no ordinary meter. This is the nicest meter I'm ever going to own. So I kind of wanted to make a big deal out of it. Not only is it an 8.5-digit multimeter, it's Fluke's best version of it. It's their metrology grade version. And that means that it's got some of the tightest specifications that you can get in one of these classes of meters. Now, I'm not going to go into the specification in any detail because it really depends on what you're going to do. There's just too much that can vary and change the specification of this meter. For example, it depends on how long it is between the measurements you're making, from the ranging from 20 minutes up to 2 years, or if you're just trying to make relative measurements or absolute measurements, or if you want to factor in temperature and any other change. And this is just the table for DC voltage, so it's absolutely insane. So all I'm going to say is it's a great meter. There are some questions about its linearity, which were discussed on the EV blog forum. But really, all I'm going to use this for is as a transfer standard. And for me, what that means is I'm going to use it to transfer the accuracy of measurements from Fluke calibration lab over into my own lab so that I can measure physical phenomena accurately and be certain that I'm measuring it relative to good definitions of, say, the voltage or the ohm and so on like that. And I'm also going to use it to calibrate some of the pieces of equipment I'm going to be repairing in the future, which includes things like an 8.5-digit calibrator and some voltage sources and some resistance sources as well. So this meter is going to be the transfer standard for my lab, and that means it's going to have to travel back and forth to Fluke calibration over in Norfolk and get its calibration verified periodically. So I'm going to need to look at something to transport it in, and of course it's probably going to be this box here. You could of course buy a proper calibration travel box from Fluke themselves, but unless you want to shell out a few thousand, you're probably going to be using the cardboard version, or trying to build your own. Thinking about it a bit more, I probably wouldn't use the cardboard one because I've got a couple of bits of piercing damage to the outer cardboard shell. So what I'd probably do is build a box as the same dimensions as the cardboard box and then use the inner packing as support inside. The inner packing's pretty impressive. You've got a huge gap between the actual meter and the outside edge, so that looks like a pretty good solution. And you've got this kind of tray of accessories just over the top here, which we'll take a look at now. Now, in this tray is the largest kind of plug I've ever seen on a kettle lead or an IEC lead. I mean, just look at that bad boy sitting there. It's just huge compared to all the other sockets that I've got. Anyway. Inside there's also just essentially some safety declarations in a printed manual, and for some reason it's wrapped in a pink anti-static bag. I don't know if that's some kind of inside joke or if they really worry about those notifications being static sensitive. There is a really nice set of leads. They're from Pomona. They have a few sets of clips on there and a set of test cables that have retractable banana sheaths on them, so they'll actually go into the meter. But then there's these two 4-wire shorts that you can see down there. Now, for some reason, I wasn't sure why they gave us two, but then I noticed that the spacing seemed a little off. It didn't seem square. And then I noticed that it didn't fit my equipment. And yeah, sure enough, the Fluke has gone and changed the spacing on the front of the meter. I mean, I've got an old 1999 Fluke 4-wire short that I use on my other meters when I'm trying to just calibrate them, and you can see it just doesn't fit the spacing. Weirdly, the sense terminals and the input terminals have a different spacing than the high-low. So you can still get most things in. If they're a 2-wire banana jack, you can get that in the right way, but not the distance between the sense and the input terminals. Just really weird. And I guess that's why they give you two, because they're such odd shapes that anything you have already probably isn't going to fit. Anyway, back to the cables. Yeah, you can see that they're really nice. They feel really nice. They're definitely high quality. You've got some point probes there with some covers over them, and then you've got these retractable sheaths, like I said. What's really nice is, yeah, that sheath comes back, and that's really useful for the kind of meters that we have, where they have these 5-way binding posts, because they're not safety banana jacks, you know. So things like this Keithley here, they're just great if you've got a set of retractable leads. You can actually plug them in and still feel like you get some protection on higher voltage connections. But they're not what we would call metrology grade cables. You know, I don't think they have any specifications regarding thermal offsets, thermal voltages developed across them. So they look silvered though, so they seem to have a silver plating on there. But yeah, I think they're just a high quality set of test leads, not a metrology set of cables. So there is a CD in there, but it's just for compliance, just like the other booklet that's in here as well. So it's containing the source code for all the open source libraries that they use inside the meter. About the only thing you can deduce from that is that it actually runs on a version of Linux called Angstrom, which is now defunct. But nothing else was really interesting that I could see digging through that. And you can see this booklet that was in the anti-static bag is really just compliance information, so safety notifications and stuff. So let's get the meter out. You can see the handles are backed by a piece of wood, so the box really is well put together. Great carry handles on there, make the carrier, whoever's delivering it, treat a little bit better if they can get a good grip of it. And then you can see it's cocooned in a really thick layer of foam, pretty robust foam as well. So I've got no concerns about this thing being delivered safely. So one of the things I noticed, apart from the cal stickers keeping the ppms in, I've actually got a calibration date of the 9th of March. That's really good because this thing got delivered on the 22nd of March. So really is quite fresh from the cal lab. And that's great because you want the thing to be as freshly calibrated as possible and not just hanging around in a warehouse, slowly drifting away from the calibration spec. The back of the meter is pretty much how you'd expect. All normal stuff in here. USB host and device is kind of interesting. GPIB. LAN is rare on some of the 8.5-digit meters. This is something that the Keysight's offering doesn't have. But otherwise, everything else is pretty normal. Aside from maybe a frequency reference in. That's a bit odd. I have to say the handles on the front of this thing and on the back of these things are beautiful. Those are the best rack mount handles I've played around with. There's a set of Tilton bales underneath, which I'm going to use now. And yeah, it's a bit of a bench hog, but nothing obscene. Got a lot of depth to it, but yeah, I think aesthetically it's quite a beautiful meter. Now we're going to do one of the most useless performance metrics for an 8.5-digit meter, which is measure its startup time. I say it's useless because if you're turning this thing off and on, then you really don't care about your calibration, because the shock of that startup is probably going to cause your meter to drift more than it would if it was just left on all the time. As you can see, this meter starts up in about 18 seconds, which is lightning fast. All of my other meters don't start up that quickly. So it's impressive they have that, especially given it's a Linux distribution, although it's sort of not very useful. Speaking of not very useful measurements, I measured the power draw while it was off, and 7 milliamps at 240 volts. That tells me that it's keeping its reference powered up, even though the clunking power switch is off. When you turn it on, it draws about 30 odd watts, but what was kind of surprising to me was the power factor. A power factor of 0.74 is pretty low for a piece of modern equipment. But there's a lot of wizardry in these kind of meters to get rid of noise from across from the mains power, so common mode noise and differential noise. And yeah, I wouldn't be surprised if that's the source of this low power factor. So let's take a quick look at the interface when you're trying to measure DC voltages. You can see it starts up, the meter actually starts up in DC voltage mode, and straight away it goes into the 1 kilovolt range. And I can change the range by pressing this button here and choose anything from 1 kilovolt down to 100 millivolts, as well as auto ranging. If I just switch this into auto ranging, you can see it'll dial itself down into the 1 volt range, and these terminals are drifting. And the reason why these terminals are drifting, and they're very sensitive to it, is I believe there's tera-ohms of input resistance on this meter when it's in auto mode. So we can actually bring that down by dropping it to a 10 megaohm resistance. And you can see that's brought us down to the millivolts. It also has a 1 megaohm resistance region. We have another control here as well, which is the resolution. We can pick that up to 8 digits. And then what you'll notice is the measurements take a lot longer. And down the corner here, we have it saying that it's going to take 10 seconds. We can alter that. So there's auto, which automatically goes to 500 power line cycles for this 10-second measurement at 8 digits. But it does have a 2-second fast 8.5-digit mode. And yeah, that and supposedly meets specifications as well. There are other menus in here that actually control the reading process. So for example, I can press this inputs button up here, and here I can change to front or rear measurement terminals. I can even do scan measurements, so I can actually do front minus rear, or front over rear, or even front minus rear over rear if I'm looking for some kind of relative measurements as well. There's also a final mode here which is isolated, and so weirdly, a bit weirdly, I am making measurements just while the meter is totally disconnected from all of its front panels. So if you're doing scan measurements, there seems to be delays here, and so I'm assuming that these are settling delays. These are delays that you can configure when it switches from back to front before it actually takes the measurement. I have an external guard here. You can see this is lit up. Basically, you can change whether you want to make the guard connection outside of the unit or inside of the unit. That's really useful for resistance measurements. When you don't have external guard on, this is actually high impedance. This isn't connected to anything. And then finally, this button over here, you have this output signal, and you can actually use the BNC at the back to provide a triggered signal whenever, say, a signal is acquired or the aperture is open. There's a few other things in here. I have a 0 button. The 0 button is when I want to zero the meter out. So you can see I have an offset now. If I put one of those shorts in, I could short the meter out, measure the 0, and then zero either this particular range, or I could zero the entire DC voltage function. I could do some math. You can see the math function in this meter is actually a bit limited. It's just a linear function here, but that gets you most of the way. So you can perform a nulling here by essentially subtracting an amount off. If I want to do that, I can actually hit last reading to immediately provide a null. That's kind of a nice convenience function there. I can normalize as well, so divide by some scale. That's really useful as well if I have something, well, I don't know, like say one of these shorts here. I could actually perform math using the rated current of this current shunt to actually get a measurement that is sensible, because this is a 0.05 ohm current shunt. So if I divide by 0.05 a voltage reading, I would actually be measuring directly the current in amps. Analyze is actually quite interesting. So what you notice is it's performing readings. If I just hit memory setup, you can see I have 26 readings in the buffer. It automatically starts storing readings straight away as soon as it starts making them. And if I hit analyze, I could actually get the statistics on those. And you can tell, you know, this has got its metrology roots. I can choose to have the standard deviation in terms of ppm or not. If I hit back, I can also get charts with the statistics, or I can just have a look at the chart itself. But there's very limited control over this chart itself. I can only choose to plot everything or just the recent measurements. And I think the recent measurements gives you the last 250 or so measurements. That's all I can do. I can have a histogram as well, but this is sort of like Keysight's modern 6.5-digit meters. They have this very limited plotting capability in here. It's not anything like the Keithley touchscreen DMMs in terms of their plotting capability. What else? Instrument setup. Okay, this is kind of interesting. I can reset the instrument, change settings such as the language and so on. I could also set up the remote connections, so GPIB, Ethernet, USB, and so on. I can adjust the calibration in here. It's password protected, but you do have the password. The service manual is online. And there's a diagnostic test I can run here, and that only takes, I would say, 26 seconds. So it's pretty good that it's so fast. Finally, we get into the trigger setup, and this is quite complex for what is at first appears to be something quite simple. So trigger events, immediate is this continuous trigger. It's just continuously triggering, but I can also trigger off bus, external, hold, internal, line, manual, synchronous, and timer. So quite a lot of configurability, and depending on which mode you pick here, you get a whole other set of options. The only thing I do know at the moment is if I go to immediate, I can change this number here and actually pick a fixed number of samples to happen when it's triggered. And this is mainly useful when we're doing digitized readings. So digitized readings is a whole other mode, but it allows me to measure either voltage or current, but it measures it at high speed. I think it's something like 5 megasamples a second. This digitized mode is not as precise as the main mode, but it is extremely fast and has a very high bandwidth. You actually even have the ability to lower your bandwidth on this. So at the moment it's got a 3 megahertz low pass filter, but you can lower that to 100 kilohertz or turn that off. In this digitized mode, you have to pick your range and stick with it because it's very fast. It doesn't have time to calculate a range change, so do an auto scaling or anything like that. So I can go down to 100 millivolts here and up to 1 kilovolt. I could also do current up to 30 amps. That 30 amp capability is quite incredible in such a meter. But yeah, and I can also pick my coupling. So just as I had the same options before in the DC volt zone. And that's it. I did notice though, so one of the things you'll see when I trigger this reading, You see that's all the measurements made. So if I go to mem setup, you can see I've made 10,000 measurements. Quite incredible how fast you can do that given the speed of this meter. So we'll make 1,000,000 just to see an effect. So they are 1,000,000. Go back to digitize, trigger that. Right, you can see that the capture takes place and then the transfer takes some time after that. If we hit mem setup, we can actually see something on the memory of the device, and we see there's volatile memory and there's non-volatile memory. Volatile memory is much smaller by about 2 orders of magnitude than the non-volatile memory. By default, the system will be storing its measurements to volatile buffers, and you can tell it to store it to non-volatile memory instead. Once you've got readings like this 1,000,000 in here, one of the things I've noticed is it's very easy to blank those readings. What you'll notice is we're actually getting some readings made on the meter now. But if I just stop the readings and then carry them on, it blanks it. So for example, if I decide to then turn timestamps on, it blanks the readings that have been taken. If I make a change, say to this 100 millivolt range, which it was already in, it blanked the readings. Essentially, whatever you do blanks the readings continuously. And that's a little bit frustrating if you're making a measurement and you want to make an adjustment while that measurement's going on. You really can't. Anyway, what you should do is instead go to mem setup and then hit save record, and that then saves that record to the internal storage. Now, you'll notice that's using the non-volatile memory. You can see that's decreasing every time I hit save. And because I've turned timestamps on, it's actually using more than you might imagine, because it has to save the timestamp as well as the measurement. You'll see those results are now in this reading table, and I can then copy these out to USB, copy all to USB if I want to as well. I can also delete all of them as well. Right, so that's memory management, that's all of the measurements. What I'm going to do now is do some DC voltage measurements, and the way I'm going to do them is using this 2-second 8.5-digit mode, usually on auto, and with an input impedance of auto as well, so there's 10 ohms of input impedance. Yeah, and everything's set to auto fast. Right, let's do some measurements. So I'm finally at the point where I can start to check out the performance of this meter, and the first measurement I'm going to make is for 0 volts. It's using these metrology grade shorts. One of the things you've got to watch out for when making this kind of measurement is that you don't develop a thermal difference, a temperature difference between any bindings you make. So for example, I'm a bit worried about the transition from the tellurium copper of the binding posts to the gold-plated copper of the PCB. And if that transition, the two transitions you have, if they're not at the same temperature, then the thermal offsets caused by those junctions, thermocouples basically, they won't cancel out. So what you can see here is I got a measurement of about 40 nanovolts, which is incredibly small, but just by touching it for a little while, differentially heating that junction, I start to see values towards 500 nanovolts. And then you'll see that it'll actually bounce back and forth as that PCB comes back into thermal equilibrium with those binding posts. So yeah, you can see that, yeah, minus 191 nanovolts there now. You can see that this thing is basically a really sensitive temperature difference measurement system. So that's why the PCB is relatively heavily coppered up. That I think they're trying to actually maximize thermal conduction between those two binding posts and get it to settle out. Anyway, what I've done is I've put the short in place, and then I've allowed the thing to come to thermal equilibrium, and then I've switched the meter on to actually see what the switch on transients are like for this meter. And then I've gone and made the same measurement using my 4-wire short on my DMM 7500 7.5-digit Keithley multimeter, and we can make a comparison of those two here. So what you can see is that the Fluke has quite a small switch on transient, but the Keithley has quite a large switch on transient. Well, I say large, 2 microvolts as opposed to maybe a couple of 100 nanovolts. The Fluke actually stabilizes pretty nicely. You're seeing I don't know, a couple of hours worth of measurements, and the Keithley does too, but over a longer time scale. If I just zoom into the Fluke data just towards the end of the run, you can see we've settled out at about 280 to 240 nanovolts of offset, and you're seeing that there's a noise of about 17 nanovolts, which is incredible, really. The precision of this thing is just insane. And that fluctuation that you're measuring there is actually noise on the internal part of the meter. Now, what we're going to try and do is understand if these readings are good, if they're inside specification. And there's two things we can look at here. First of all, the size of this noise compared to the measurement precision that we're expecting, and also the drift between these two measurements. These measurements were made 2 days apart, so I can get an idea if that 40 nanovolts of change in the actual overall offset is a problem, if it's within spec, and whether that 17 nanovolts is also large compared to the specifications for the meter. So when I first recorded this, I tried to compare the noise specifications against the actual confidence intervals that have been given in this table, but that's entirely the wrong idea. At least you can see that the drift I'm seeing is about 0.4 ppm and the noise is 0.17. But these aren't really the right things. The drift perhaps, but I'm not really looking at the right specifications here for the zero drift. But the noise definitely not. This isn't something you can compare here. However, I did find this paper on the performance of 8.5-digit where their inputs shorted, and what you can, I've plotted the 2 points that I think this Fluke is landing on, depending on how you define the signal. Depending on whether you define it as peak to peak being 100 millivolts or peak to peak being 200 millivolts, given that the Fluke has 100% overrange in this 100 millivolt range, so it can measure up to 200 millivolts. But anyway, it lands pretty much where the 8.5-digit spec would go if you extended it out to 2 seconds, and well above the measured performance given in this paper. So yeah, I am happy with that. Now, until my calibrators are repaired, I don't have very good sources of stable voltages or configurable voltages. But what I do have is this LM399 voltage reference board that I bought off an EEV blog forum member. So my idea is to actually measure this on one meter and then verify it on my other meter. So what I did was I just attached the best set of cables I had, but not really a very good set of metrology grade cables. By environmental chamber, by the way, I just mean a polystyrene box you'd use to transport chemicals. And then I covered it in gel packs. And the reason why I put the gel packs in there is to put a large thermal mass inside this chamber. And that would mean that any temperature changes would be slowed, as they would have to change that thermal mass as well. Anyway, that allowed me to at least make a measurement of a modern Zener-based reference, even if it is a reference used for, say, a 6.5-digit meter rather than an 8.5-digit meter. Now, to get something I can compare against, I'm following the lead of Mr. Carlson and one of his epic repairs where he repaired a DC null voltmeter. And in that particular piece of equipment has a voltage reference inside of it, and it's actually a mercury battery. And that battery is, indicated on the schematic here. It's BT5, and it's meant to give a voltage of 1.35 volts. Now, you can't get mercury batteries anymore. So what Mr. Carlson did is he put 2 silver oxide button cells in there.
See down on the bottom there. That is the original mercury battery holder for the null. Of course, those batteries are no longer available. So that's just holding the new silver oxide button cells.
And so I thought, well, are they good as a reference? What properties do they have that makes them a good voltage reference? So I decided to measure it exactly the same way I measured the LM399, but in a slightly different environmental chamber for this one. Just push it into a roll of neoprene that I have for sealing some the electronic nose. With a tissue to help kind of cut down on drafts, and then left it like that as well. So we can see the LM399 essentially settles down after a very quick transient to fluctuate within about 2 ppm of its value. So that's pretty nice, given it's 20 microvolts on a 10 volt standard. The SR44 actually has a much larger change initially, and that's due to the discharge curve of the cell being followed. And you might have noticed I had a 68K resistor on there, and that was because I wanted to get over this initial discharge curve and get out to this more level period at the end. But you'll still notice that there's some fluctuations there, and that's usually due to temperature variations in the room. So you can see that this cell actually is fairly sensitive to temperature. This causes it to vary by about 100 ppm over its range. So it's not very good as an absolute reference, but it could work in a pinch. Noise-wise, we're just picking up the internal noise of the meter on both sources, really. It looks like the SL44 has much less scatter than the LM399 runs that I measured, but in fact that's just because of a range change. It's really nice that this meter has 100% overrange on all of its ranges, so its 1 volt range actually goes up to 2 volts, so it can fit that 1.5 volt cell in there, until you get actually the noise of the 1 volt range rather than the 10 volt range that's used for the LM399 reference. So the next mode I want to kind of show you is resistance measurements. You have the same thing as before. The meter starts up, it goes to its high resistance range. So we'll just quickly change that to auto. And we have 7 or 8 digits, so we'll turn 8 digits on. But then we get this mode here. And this mode here has quite a few modes, even more than the Keithley does. So there's a 2-wire normal mode where it measures resistance just on these 2 terminals. And then there's the 4-wire normal mode. But then there is a 4-wire true mode. Now in 4-wire true, you're going to hear the meter start clicking. What's happening here is these force terminals where your current is sourced, their polarity is being reversed. The voltage difference you're sensing corresponding to that current is reversing as well, right? The difference in that. So if you have thermocouple effects, so voltage offsets at each junction here, they don't change polarity, but the actual thing you're interested in, the voltage arising because of the current sourced, that is changing sign. So you can deduce that. Now, this is usually called offset compensation on the Keithley meters, and it doesn't click. The Keithley meters don't click. They use some solid state switching in their meters. And I'm a little bit nervous whenever I hear relays click in a device, because I know that relays have a finite lifespan. So I'm just going to pop this back to 4-wire normal for now. But we will do all of our resistance measurements in that 4-wire true mode. There is another mode in here, another 2 modes, which is a 2-wire and a 4-wire HV, which is a high voltage mode. And what you can see here is if I hit that, you can see I get a little, electrocution warning sign, and I see a little flashing 200 volts. And basically what that means is we're going to try and provide 10 microamps of current on these terminals. And in order to make that happen, there is a compliance voltage of up to 200 volts. So these terminals now are live. They're actually at 200 volts. When you go into this high voltage mode, then all of a sudden you can access the very high resistance ranges of this meter, all the way up to 10 gigaohm. There is one other thing here as well, which is this low LOI. This is the low current, so I for current mode. And what you'll notice is, say we're in this 10 kiloohm range, we're currently going to measure current as 100 microamps and a compliance voltage of 2 volts. If I turn on low I, what you notice is that drops by an order of magnitude to 10 microamps with a 200 millivolt compliance voltage. And the idea of this low I mode is that you are trying to prevent heating in the device that you're measuring. And that's it. Everything else that we've seen is the same. So for example, I can do guarded measurements. Guarded measurements for resistance are a lot more complicated and probably even more valuable. But I'm not going to do them here. I don't quite have the setup for that yet. I need to get a chamber that I can do measurements in, and that's going to be the subject of a whole other video later down the line. So next I'm going to try measuring some resistance standards. I've got a 0.01 ohm Leeds and Northrop resistance standard here. I've put it inside the polystyrene box, mainly just to keep it upright rather than actually isolate it from the temperature. I've put a platinum resistance thermometer into a little well that's inside there. You're meant to add some kind of fluid to help bond that thermocouple thermally to the actual system. I haven't done that, so it's not a particularly accurate measurement, but we're getting about 22 degrees here. The main thing I wanted to make sure was that the whole system was roughly around the calibration temperature of 23 degrees C. Supposedly my lab average is about 23 degrees C, but I'm measuring it with this very cheap temperature, humidity and clock thing. So at the moment I believe the platinum resistance thermometer, that 22 is probably more about right. And you could see the voltage that the resistance we're measuring there is brilliant, but that's on the 1k ohm range, or is that in the 1 ohm range? No, that's in the 1 ohm range. And now I've just put it up to 8.5 digits, and you can see it's giving me a 0.01 ohm, and then some change, and the change is in the nano ohms region, 38 nano ohms. So very happy with this. I have some other resistance standards. This is my 1000 ohm standard here, and I have a 10,000 ohm as well. What's really nice about this is this one has a measurement of 1 ppm out, but this measurement was made back in 1984, so this calibration is as old as I am, if not a bit older actually. So we'll give that a go next. So in setting this measurement up here, I'm being a little bit slapdash. I'm meant to be making measurements at those screw terminals that you see, and I can do a 4-wire measurement. The outer terminals are for the force and the inner terminals are for the sense. But instead what I'm doing here is just clipping my clips straight onto that bar. I could try and make measurements like you see here, but you see the clips don't quite mate it on top of that. There are some other issues as well with the standard. It's got quite a patina of oxidization on it, and I haven't really cleaned that off. The reason why I haven't cleaned that off is because I'm a little bit nervous about what that might be. Some of these resistance standards, they used to be measured by dropping them into cups of mercury, so those arms would hang over into cups of mercury. And so it could be that there's mercury on this, and that, you know, could be organic mercury. I don't think it is. It's a green corrosion, so I think it's just copper, and it's a plated copper that you see here, probably silver plated copper. But yeah, I'm a little bit nervous about making too much attachments to it, so clips for now it is. And as you can see, I'm getting a pretty good reading. I'm reading well within, well, what's that, 7 ppm. I'm within 7 ppm of that original measurement. I'll wait for another cycle to come through now. Yeah, 7 ppm. So pretty happy with, given this is as old as I am, and it's 7 ppm out versus 1 ppm out. So we're going to test my 10 kilo ohm standard. You can see this is 98 ppm out, so just 0.98 ohms out. And that's what we're reading, 0.86 ohms out. So 98 ppm out to 86 ppm out. This is all pretty good. They seem to be drifting a little bit, but yeah, I'm very happy that these standards are okay. So I'm currently playing around with the capacitance mode on this meter. And when you get to capacitance mode, you pick more and then capacitance. You only get a few choices here. The range goes from 1 nanofarad up to 100 millifarad. And you can then choose 4 or 5 digits of resolution, and of course the low current mode. But what you'll notice is it's hard at first to get a reading out of this, and you can see the issue is one of kind of shielding and grounding. So even though this is a 2-terminal measurement, you can see that this box, this capacitance box, is not able to measure the residual capacitance of it. However, if I just take this box and I place it on the chassis, all of a sudden I can actually read that just fine. So it's about grounding for this box here that seems to be quite sensitive to, which is quite surprising given that I've been playing around with my other LCR meters on this box, and they measure quite well, or quite easily, this without any special precautions. Right, so I've got currently this in a banana jacks to BNC, and then into this box, transition back to banana jacks. And if I want to try and read this, I can also try and adding a ground lead here, and that grounds the case as well and gives me a nice reading there. Now what I should say is I've already put this box on, and then they recommend that you zero the meter while it's in its reference position. So they actually say that you should zero it with one of these terminals disconnected. And I've not done that in this case because I want to actually just dial in the capacitance straight away here. So I want to zero out the residual capacitance on this box. So we could just see what happens as we kind of dial along here. But you can see here it's picking up straight away. This is 900 picofarads or 0.9 nanofarads. So that's just fine. And I'm getting a 9 there. Yeah, looks pretty good. Actually, the capacitance added here is pretty good. That's actually below, well, just about 1%. That's actually better than I thought this box was. Yeah, okay, here you're seeing variations of 0.5%. That's nice. And then we hit a measurement error, but then it does a range change and it's okay. Yeah, about 4.4% error here, and then about 1%. There we go, 1, 2, 3, 4. It's actually a 11132, but there you go. Okay, so capacitance mode is working, but how do we know if it's precise? Because this capacitance box isn't particularly precise. So if we want to get more precise, we can try and use some of these standard capacitors that I have, and I have them going from 1000 picofarad down to 0.01 picofarad. But I have to say it's extremely challenging to measure such low capacitances correctly. You have to offset everything, and very carefully. And one of the ways you can do that is thanks to the actual connections that we have on these capacitors, and that's the same as the actual connecting end. The connecting end looks like this. It is a General Radio GR874. And these connectors have been designed so that you can take two of these connectors and then just rotate them, place them inside of each other, and force them together. So here is my attempt to wire this capacitor up. I've had to transition from the GR, a grounding terminal connected to the ground, and then that then comes up to the two measurement leads that comes over to here. And you can see we're getting about 0.8 nanofarads. Now, I suspected the capacitor perhaps, but when I make a proper measurement using a 4-wire connection technique, using my LCR meter from Isotech, or GW Instack actually, then I get about 1,000 picofarads on the nose. And that's also true when I use my Applin 8.5-digit meter. By the way, that's a beautiful meter on the inside. It's all through-hole construction. Just for fun, I also did a measurement using my DIR EE, and provided I used the guard terminal, I could get that about 1,000 picofarads as well. So I'm not really sure what's going on there with this meter. It's probably the connections, but if you read the manual says that the standard lead set can be used for most capacitance measurements. So I'm not sure if I'm just kind of have a bad environment for this, or the way it's the measuring, but I can't seem to get good results for that. Needless to say, I don't think you're buying this meter to use its capacitance function, so I'm not really too worried about that. Now, next up is DC current measurements. To kind of provide a basis for comparison, I'm going to use these beautiful old current shunts. This is a 30 amp shunt from Pi & Co in Cambridge. Probably, again, older than me. I know one of them was calibrated in 86. You can see it's a 4-wire shunt. You've got the two power terminals on the outside and then two sense terminals on the inside, and it seems like you can even calibrate these things by just adjusting where the wires are actually soldered on. It seems that's been done in the past. I'm not going to do that though. What I'm going to do is just do a 4-wire measurement to determine the current shunt's resistance. That's perhaps not the best resistance to measure. You might want to see what the resistance is once it's hot or at its operational current, but it'll do for now. We're just playing around in all of this really. So yeah, I'm going to get a precise 8.5-digit measurement of its resistance, and I've got a second shunt, but I just want to show you that this 13 amp shunt, the main thing I want to show you was the calibration date. You can see this was calibrated in 87, so we know this is at least as old as 87. I can't believe this is a 1 ohm shunt as well. I can't believe how little I paid for these. I paid £10 for them, for the pair on eBay. Such a brilliant steal. Anyway, I've got those two measurements, so now what I can do is actually use the Fluke meter in current shunt mode. So it's going to make a voltage reading, but I can program in my shunts to actually get it to calculate the current for me. And you can see I have to take the information of the shunt, and I can then dial it into a list of shunts. And you can see I've entered in the 30 amp shunt there with its notional resistance. What's kind of cool about this, it has all the normal options, you know, range and so on, only up to 10 volts, and only up to 7.5 digits. And I could also pick certain readings, but there seems to be a firmware bug. The only way to actually get it to change is to use the buttons along the bottom rather than the select. Anyway, if I do all of that, then I can make current measurements using the shunt. And what's kind of nice is it actually does some compensation for the input resistance of the meter even. So I think that's one of the things you can say there with shunt corrections. Right, so we're ready to try and get this to work. So I'm going to use my Isotech IPS 3072 amp power supply here. I didn't think much of these power supplies. That it was from GW Instack. They do make really good equipment, but I didn't really think much of these until just recently when I noticed that Keithley is actually rebranding these as reselling these, even though these power supplies have been around for years now. Anyway, I'm just going to put an amp in, and you can see the shunts reading 1.01 amps. So I'm just eking my way up in the current here, going up to 10 amps, basically through nerves. Yeah, I'm a bit scared of blowing up the meter somehow or blowing up the shunt. I've never really taken it to high power yet. So at 10 amps though, everything seemed pretty good. You can see getting a reading of 0.5 volts, whereas I'm driving it with 0.6 volts, so I'm getting a bit of loss in the lead. And then eventually we take it all the way up to 30 amps, and you can see we're reading that value there. Now what we're going to do is verify that against the internal current shunt. So we're going to take the internal current shunt mode and measure the current of this meter and just see if they agree. So we're just about to route the power supply straight through the Fluke meter. I haven't kept it in series with the shunt. I probably should have done that for a better reading. But you can see here at 10 amps, we're reading pretty much exactly the same reading. I mean, within the fluctuation, and that's probably just the settling of the supply. So I felt confident to take this up to 30 amps. You notice now I'm disabling and enabling the output current so I don't overshoot accidentally. And you can see there, again, once it settles down a bit, we actually seem to be approaching very similar values, or at least within about 5 digits, the fluctuations in the 6th digit. So I'm very happy with how these old current shunts are performing, and also how the the power supply itself is performing. So there it is. I hope you enjoyed looking at the Fluke 8.5-digit multimeter as much as I did. I can't really measure its performance in any meaningful way. I just have to trust the datasheet, but I think coming from Fluke, that's probably something you can do. There are still some questions that I have about this meter and its performance, particularly around linearity and how it behaves as we try to measure across the scale. I also am still puzzled by the choice over, changing the spacing of the binding posts. I'd love to know what the story was behind that. That seems a little odd. There are a couple of bugs in the firmware as well, but taking that all together actually was really a dream operating a meter like this. Its actual interface is leaps ahead, I think, of the 8.5-digit, while it might still lag behind in some other aspects, like being able to access data from ACAL observations inside of it, which allow you to kind of do some diagnostics. There might be something that you can do with the 8.5-digit in that respect, but I haven't seen it. Another thing is the questions around linearity of the meter. Specifications around that aren't really very clear, so it'll be interesting to see how that develops. But overall, I really do like the meter, and I hope this video helps you understand what this meter is like to have, because when I ordered this meter, it wasn't clear to me what the interface would be like or how it would be in operation. So hopefully I've managed to cover that at least for you. In the future, I'm going to use this for all sorts of experiments. I'm building what's called a transient heated wire apparatus. This is something I built with one of my undergraduate students. This will allow me to measure the thermal conductivity of gases. You can see essentially this is the sense board, and it's inside a flow cell. That's one of the things that I've got this meter for. I want to use its precise resistance measurement and its digitization capabilities in that one there. In the future, I'm going to repair the calibrators that you've already seen, but I'm also going to try and repair things like this 1 ohm standard, unfortunately, that was damaged during shipping to me. And so we're going to see if we can actually restore this 1 ohm standard back to its previous excellent measurements. And we have the old test measurements here. I'm also going to build in the future a calorimeter, a drop calorimeter, and so you can see I've been buying tech plates to use as heat flux sensors, as well as lots and lots of liquid cooling systems, which I'm going to use to create a very stable chamber that I can then use to do calorimetry in. If you've noticed that I've done something wrong, then don't stay quiet about it. Put it in the comments. I'd love to hear from you. Metrology is a science where you're always learning, and I feel like I have quite a lot to learn, so it'd be great to hear what your thoughts are. Right, see you next time.